Our journey begins with a simple yet extraordinary phenomenon: evaporation. Picture a sun-drenched lake, its surface shimmering with warmth. The sun's energy excites water molecules, giving them the power to break free. They rise, transforming into an invisible vapor. This process isn't limited to bodies of water. Plants release water vapor through transpiration. Just like we perspire, plants contribute to the moisture in the air. Think of vast forests exhaling a constant stream of invisible vapor. The oceans are the true giants of evaporation. Covering over 70% of our planet's surface, they release colossal amounts of water vapor. It's a constant exchange, driven by the sun's energy. Evaporation is the engine of the water cycle, lifting billions of tons of water into the atmosphere. As water vapor ascends, it enters a world governed by different rules. Here, temperature and pressure decrease with altitude. The air, warmed by the Earth's surface, acts like a giant hot air balloon, carrying the invisible cargo of water vapor higher and higher into the cooler reaches of the atmosphere. This upward movement, driven by temperature differences, is called convection. Imagine a pot of boiling water. The hot water rises, cools slightly, and then sinks back down, creating a continuous cycle. Similarly, warm, moist air rises, cools, and eventually releases its precious cargo back to Earth. But how does this cooling lead to rain? The answer lies in a fascinating phenomenon known as adiabatic cooling. As air rises and expands in the lower pressure of the upper atmosphere, it loses energy and cools down. This cooling is crucial because cooler air has a lower capacity to hold water vapor. As the air continues its ascent and cools further, it reaches a critical point, the dew point. This is the temperature at which the air can no longer hold all its water vapor, and the magical transformation from invisible vapor to visible water droplets begins. Condensation. The process of water vapor turning back into liquid water is at the heart of rain formation. As the rising air cools past its dew point, the excess water vapor seeks out tiny particles in the atmosphere, such as dust, pollen, or even sea salt. These particles act as condensation nuclei, providing a surface for the water vapor to cling to. Imagine each particle as a tiny seed, attracting more and more water molecules until they grow into visible water droplets or ice crystals. This is the same principle behind the dew that forms on grass in the early morning, or the condensation that forms on a cold glass of water on a humid day. The size and state of these condensed water particles depend on the temperature in the atmosphere. If the temperature is above freezing, the water vapor condenses into tiny liquid water droplets. However, if the temperature is below freezing, the water vapor can transform directly into ice crystals, a process called deposition. This process of condensation, driven by cooling temperatures and aided by condensation nuclei, marks the crucial turning point in the water cycle. The invisible vapor, carried aloft by rising air, begins its transformation back into a visible form, ready to return to the Earth. As more and more water vapor condenses around these nuclei, they clump together, forming the familiar sight of clouds. Clouds are not simply masses of water vapor, they are intricate collections of billions of tiny water droplets or ice crystals suspended in the atmosphere. The type of cloud that forms depends on the altitude and the temperature at which condensation occurs. High-altitude cirrus clouds, for example, are composed of ice crystals and appear as delicate, wispy streaks across the sky. Lower-altitude cumulus clouds, on the other hand, are often puffy and white, formed by water droplets and often associated with fair weather. Towering cumulonimbus clouds, however, are the giants of the cloud world, reaching high into the atmosphere. These clouds are capable of producing intense thunderstorms, heavy rain, and even hail. Their dark, menacing appearance is a clear sign of the powerful forces at work within them. Clouds, therefore, are not just beautiful and ever-changing decorations in the sky. They are dynamic, constantly evolving indicators of the processes happening within the atmosphere, a visible manifestation of the invisible dance of water vapor, temperature, and pressure. The water droplets or ice crystals within a cloud are in constant motion, colliding and merging with each other. This process, known as coalescence, is essential for raindrop formation. As smaller droplets collide, they combine to form larger droplets, gradually increasing in size and weight. Imagine a crowded dance floor, with dancers bumping into each other and forming larger groups. Similarly, within a cloud, countless tiny water droplets collide, merging and growing larger with each interaction. This process continues until the droplets become heavy enough to overcome the upward force of the rising air that initially carried them skyward. At this point, gravity takes over, and the water droplets begin their descent as rain. The size of a raindrop can vary greatly, from a fine mist to large heavy drops. The intensity of the rain is determined by the size and number of raindrops released from a cloud, which in turn depends on factors such as the amount of moisture in the air, the strength of the updrafts within the cloud, and the temperature profile of the atmosphere. Beyond rain, a world of snow, sleet, and hail. Rain is just one form of precipitation, the collective term for any water that falls from the sky. Depending on the temperature profile of the atmosphere, precipitation can take on many forms, each with its unique characteristics. Snow, for instance, forms when the temperature in the atmosphere is below freezing, and the water vapor deposits directly onto ice crystals, bypassing the liquid stage altogether. These ice crystals grow into intricate, six-sided snowflakes, each one unique in its delicate structure. Sleet, on the other hand, forms when raindrops fall through a layer of freezing air near the ground. The raindrops freeze into small, translucent ice pellets, creating a sound like tiny pebbles hitting the ground. Hail, a more dramatic form of precipitation, forms within thunderstorm clouds, where strong updrafts carry raindrops high into the freezing upper reaches of the atmosphere. These raindrops freeze, collecting layers of ice as they are repeatedly tossed up and down within the cloud by the powerful updrafts. Eventually, they become too heavy for the updrafts to support, and they fall to the ground as hailstones, which can range in size from small pebbles to large grapefruit. El Niño and La Niña global dancers shaping rainfall. While the basic principles of rain formation remain constant, the global distribution of rainfall is influenced by a complex interplay of atmospheric and oceanic patterns. One of the most significant of these is the El Niño Southern Oscillation, or ENSO, a recurring climate pattern characterized by changes in the temperature of the surface waters in the tropical Pacific Ocean. El Niño, the warm phase of ENSO, is characterized by unusually warm surface waters in the central and eastern equatorial Pacific. These warmer waters disrupt the normal atmospheric circulation patterns, leading to shifts in rainfall patterns across the globe. La Niña, the cool phase of ENSO, is characterized by unusually cool surface waters in the same region. Like El Niño, La Niña also disrupts normal atmospheric circulation patterns, but with opposite effects, bringing increased rainfall to some regions and drought conditions to others. These large-scale climate patterns highlight the interconnectedness of our planet's systems, demonstrating how changes in ocean temperatures in one part of the world can have a ripple effect, influencing weather patterns and rainfall amounts thousands of miles away. Atmospheric rivers, mighty sky-high waterways. Imagine a river, not flowing across the land but high in the sky, carrying vast amounts of water vapor. These rivers in the sky are known as atmospheric rivers, narrow corridors of concentrated moisture in the atmosphere, typically thousands of kilometers long and hundreds of kilometers wide. These atmospheric rivers form when strong winds transport large amounts of water vapor from tropical regions towards higher latitudes. When these rivers encounter mountains or other topographical barriers, the air is forced to rise, cool, and condense, releasing its moisture as heavy rain or snow. Atmospheric rivers play a crucial role in the global water cycle, transporting vast amounts of water vapor from the tropics to higher latitudes, where much of the world's population resides. While they are essential for replenishing water supplies, particularly in coastal regions, they can also cause devastating floods and landslides if their moisture release is too intense or prolonged. Understanding the dynamics of atmospheric rivers is becoming increasingly important, especially in the context of climate change, as changes in temperature and atmospheric circulation patterns could potentially alter their frequency, intensity, and paths, with significant implications for water resources and natural disasters. The lifeblood of our planet, rain's vital role. Rain, a seemingly simple phenomenon, is a fundamental force that shapes our planet and sustains life as we know it. It is the lifeblood of our ecosystems, replenishing rivers, lakes, and groundwater aquifers, providing the essential ingredient for plants to grow and thrive. From the lush rainforests to the arid deserts, all ecosystems depend on the delicate balance of rainfall for their survival. Rain nourishes our crops, provides drinking water for humans and animals, and plays a critical role in regulating the Earth's climate. The next time you feel a raindrop on your skin, take a moment to appreciate the incredible journey it has taken, from the vast expanse of the ocean to the cloud-filled sky and finally back to Earth. Rain is a testament to the interconnectedness of our planet's systems, a powerful reminder that even the smallest raindrop plays a vital role in the intricate web of life on Earth.